Well, really pleased you're all here. We're very excited for this week, and we're really excited to start with Melanie Matchett Wood from Harvard, who's going to tell us about statistics of number fields, function fields, and three-manifolds.
All right, thank you. Thank you for inviting me to be part of this. So, what I'm going to talk about is a little farther afield from the central theme of the conference, but I hope in the big picture, part of the takeaway can be you can see in some story how ideas and information have gone back and forth between trying to understand things for number fields and for three-manifolds. Yeah, so I usually do not have trouble reading on the top of a board. Okay, so next. Function fields. So first, I want to introduce the topic, the question of class group distributions, which is a central area of study in arithmetic statistics, sort of part of number theory that tries to understand of the number theoretic objects out there, how many of them are what kind of things. And so the vague question about class group distributions, maybe I need some notation before I have the question. So if I take a number field, so a finite extension of the rational numbers, for each number field, there is an associated finite abelian group, the class group, which controls the arithmetic of the number field, in particular, measures the failure of unique factorization in its ring of integers. But for the purposes of this talk, it's fine if you just also abstract away and say, okay, for each number field, we get some finite abelian group that we care about. And the question is, as k varies, how is this class group distributed? How, we know all the finite abelian groups. So it's really easy to sort of imagine, okay, you have different groups, like how often do you get Z mod 9? That's one of the finite abelian groups. How often do you get, Z mod 7 cross Z mod 7? That's another finite abelian group. Or maybe you could ask other questions that are, how often do you get a group whose order is divisible by 5 at all? So any of those questions are in this spirit. More precisely, okay, as k varies over what, we usually fix G, a finite group, and k varies in some family of G extensions, so Galois extensions with group G, so say k varies over extensions of some fixed field, k naught, some fixed number field here, k naught, and k, so this will be fixed, and k will be varying over all the G extensions, and also usually with some fixed behavior at infinite places. which you don't have to worry about so much, and then we order all the K that are Gaussian extensions of K naught in some way, say maybe by the size of their discriminant or some other invariant, and that gives a list of class groups, and then in some say natural density, you could ask, well, what is that distribution you're seeing? For example, we take the group of order 2 and K naught to be Q, and what I would mean here by some fixed behavior in infinite places is we could take the family of real quadratic fields. Okay, so these are just Q adjoin the square root of D as D ranges over positive square free integers, and each of them has a class group, and we can say, how is that distributed? So in the 80s and 90s, Cohen, Lenstra, and Martinet made conjectures for the distribution of class groups in these families, like I mentioned here, for these distributions. Suffice it to say that we know very, very little towards these conjectures. There has been a lot of work and some small amounts of progress, but these proving these distributions still seems to be an incredibly difficult thing to do. But carrying on the example here. So this is what their conjectures say in this example for real quadratic fields. They conjecture that the probability that your class group, well, I'm just going to take the odd part of the class group. So it's a finite abelian group, and so you can just take this quotient by all the 2 power torsion, for example, because of this 2, something strange happens there. But the probability that you get a particular group here, they write, this is a conjecture, exact formula. So on the top, I'm going to have some number, a product over primes bigger than 2, and then a product over I, 1 minus p to the minus I. So that's the number. It doesn't depend on A. And in the denominator, I have the size of the group A and the size of its automorphism group. So this implicitly is some limit as this D as a bound on D goes to infinity, and you take a uniform random field up to some bound, and then there's an implicit limit as that goes to infinity. So it turns out this does give a probability distribution on finite odd order abelian groups. They came up with this distribution by looking at tables of class groups. There were, there are very efficient algorithms to compute class groups of quadratic fields. So even back in the 80s, there were a lot of tables, and so there was a lot of data, and part of their motivation for proving these conjectures was trying to explain the tables and why some things were occurring more than others. For example, why you saw a Z mod 9 so much more often than you saw a Z mod 3 cross Z mod 3, even though they're the same size. And this automorphism factor is contributing towards explaining that. And that also was a major sort of piece of the philosophy, was that things should occur in nature inversely proportional to the size of their automorphism groups. And so this, that was a major philosophical motivation for the conjecture. And so, all right, so in the time since then, there has been some small progress towards these conjectures, but also realizations that several things are wrong with them. So I still think I would still bet on this one, but the more general conjectures that are for every Galois group G and with fixed behavior at different places, the general conjectures have some issues. So in 2008 and 2010, Guatemala, who had done a lot of computations to look at tables of class groups, had data suggesting that the conjectures were wrong for the P0 subgroups of the class group when P divides the number of roots of unity in the base field. Okay. So this is the number of roots of unity. So here in this example, I said, well, we threw out 2 because 2 divided this 2, that was the order of G. That was a separate thing. It also turns out that Q has 2 roots of unity, but we didn't see that issue in this example. It's part of why I say I would still believe this, because we threw it out from the statement for a different reason. But in any case, if you if you make the analogous conjecture, but now, for example, your base field contains the 3rd roots of unity, Mala's table suggests that the conjecture for the 3 part, Mala's table suggests that the conjecture for the 3 part is wrong if instead of taking extensions of Q, you took extensions of Q adjoin 3rd roots of unity. All right, and so there was since then, there's been a lot of work to try to understand what is going on with roots of unity in the base field, why they were making a contribution, and how the conjecture should be corrected. This was suggested not for a theoretical reason, but just for an empirical reason. It looks like the averages are different, and they looked in the certain measurements that Mala was making, they look to be quite definitively some other number, like if the conjecture for some average was 1.5 and they were really looking like they were going towards 1.25. So it's like, okay, it's another number. It's so part of a lot of our understanding of how theoretically to understand what roots of unity have to do with anything has come from study of the function field analog. So what is that? So when I started, I said, oh, we're talking about number fields, finite extensions of Q. But in this whole story, we could replace Q with FQT, the field of rational functions over a finite field, FQ. So FQ is a finite field, and FQT is the field of rational functions. Then in this whole story, one can be talking about finite extensions of FQT, and then you fix one K0 finite extension of FQT, and you can be asking the same question. And we know in number theory that there's a very strong analogy between the number theory of number fields, finite extensions of Q, and function fields, finite extensions of FQT. In fact, a lot of times we prove things for all global fields together, putting these cases all under the same formalism. However, there is this additional great tool that one has in this case. So, right, in the number field case, we have Q, and then we took maybe some base fixed extension K0, and we're taking finite extensions K of that. In the function field case, we can do the same thing and make this same field picture. But on the function field side, these are all now fields of rational functions on curves over FQ. And so there is another piece to the story in the function field case, which is the algebraic geometry of curves over FQ. So this now now, K0 is the function field of some smooth projective curve C0 over FQ, and K is the function field of some curve C, and this inclusion of fields corresponds to a map from this curve to that curve. And so one big advantage of this picture and why we have been able to prove more and understand more on the function field side is through using the algebraic geometry of these curves. And so let's say geometry of maps of curves. And another big advantage to this situation is that this FQT, this is not a single field. It's actually, there's lots of finite fields. So there are lots of things that you can put here, one for every power of a prime. As Q goes to infinity, as the size of the finite field gets larger, in a lot of ways, the algebraic geometry becomes more like the algebraic geometry over C, and you can use more classical algebraic geometry. And I'll just say use many Q and send Q to infinity, which also makes what you need to understand from the algebraic geometry side easier. And I'll just make a note about like sending Q to infinity. There's lots of different ways that people send, you might send Q, which is a power of a prime, to infinity. Sometimes you might think I'll fix a single prime and take more and more powers of it. But that's just only one way. It could be, e.g., as Q could just always be a prime and going to infinity. Or it could go through powers of a single prime. There's lots of ways that Q can go to infinity. And that's important, especially here, because if we care about a question like whether a field has pth roots of unity, the number of roots of unity of these fields here will generally be Q minus 1. And so we want to send Q to infinity in some way such that we're controlling what what's dividing Q minus 1 if we want to understand some question here. But one has the flexibility to do that. And I should say that without Also, in the number field, original number field question, or the function field question, there's also a natural generalization. So the class group is the abelianization of natural, sort of generally most often, maybe say, non-abelian group, which on the number field side, we would often write like this: the Galois group of the maximal unramified extension. But on the function field side, one might just write it as the fundamental group of the associated curve. So now there are lots of questions, there are lots of precise details that one has to think about when you make the analogy of the class group, whether, like, which thing did you want? Did you want the thing that was like the class group of a ring? Did you want the Picard group of the curve? Do you want Picnot of the curve? So there are a lot of places where you have to be careful in your number field, function field analogy. I won't get into those weeds. So if you're worrying about one of those, which did you mean? Like, you could mean any of them. It depends on what you want and what you want the analogy to be. And you can ask about any of those. The distribution of any of those groups that are associated to the curve. But now that if we're thinking about the function field analog, this is the tau fundamental group of a curve over FQ, and that itself is a sort of natural invariant as a curve over finite field ranges in some family that you could ask about the distribution of. So more generally, we ask about the distribution of these groups, and these groups, their abelianizations are the class group. So this is just a strictly more general question that abelianize. In this function field analog, people have been able to use this algebraic geometry to see more about what's happening. So, for example, Jeff Otter in 2006, so studying the moduli space of hyperelliptic curves. So these hyperelliptic curves are what hyperelliptic means on the field side is that they're quadratic extensions of FQT. So this is looking a lot like our first example of quadratic fields. So it's the function field analog of that. So studying so we have this moduli space of curves, and for each of them, we want to study something like their class group. And so over this moduli space of curves sits the Jacobian of the universal curve. So in this moduli space, every point corresponds to a curve, and then above that, you have the Jacobian of that curve in a family, and then more precisely, he was studying the finite cover that would tell you about the L to the K torsion in that Jacobian. So that Jacobian is some abelian variety, and so it has some points who are, you add them to themselves, L to the K times, you get the identity. So that that is some piece of this family of Jacobians of this moduli space of curves, and then by studying how the fundamental group of this moduli space acted on this moduli space, which you can just think of as, well, what happens, if I have in the fundamental group, if I have a loop down here and I follow it and I upstairs and I see what it did. So he used the monodromy, which is the image of the fundamental group of this moduli space of hyperelliptic curves downstairs, and how it acted above. So that gives a representation or a map to the general linear group of some dimension, depending on what the genus of the curves here was over, say, Z mod L to the K, since these are L to the K torsion points. And using that, he could see that as Q goes to infinity, remember I mentioned that is a sort of useful tool there, that as long as L does not divide Q minus 1, which is another way of saying that we're talking about a part of the class group that is relatively prime to the number of roots of unity in the base field, that we get a distribution matching the conjecture. So the appropriate, there's some small tweaks to in this number field function field analogy, but essentially morally you can think of as like matching the numbers that you would get here. All right, so that used a Chebotarev-like theorem that said that the Frobenius would be equidistributed in the image of this map here, and an understanding, again, of the algebraic geometry and topology of the moduli space of hyperelliptic curves, and then it told us something about the distribution of these class groups, and
so in that case, do you
Yes.
have this geometric interpretation of the numerator or the formula?
A geometric interpretation of the numerator. I mean, I think not exactly a geometric interpretation. One still has that same numerator. How you could see it coming out of something like this, I mean, just to, all right, so you have here I called this the L torsion, I guess, because and the prime that used to be P, once we could go over function fields, people want to call L because you usually think of P as the characteristic of FQ. So sorry for that slight shift. But okay, there's some factor that appeared in the numerator that looked like this. There was a question, is there a sort of geometric interpretation of that? I think maybe not, I wouldn't call it a geometric interpretation, but you can see numerics of this coming from something like what happens when you map into a group like this. So for example, I mean, even though this isn't exactly what's going on here, but a good example to think about is if you wanted to think about if you had a random matrix in here, what the probability would be that it would be full rank. You would say, okay, well, the first row should not be all zeros. So that's probability one minus L to the minus 2G. And then the next row should not be in the span of the first row. So the probability that the next row is not, the second row is not in the span of the first row is that. And then you continue on like that, and you can see sort of this kind of constant appearing, basically more from the algebra of the matrix groups than from geometry, I would say. Okay, so I'll mention that in 2016, Ellenberg, Venkatesh, and Westerland proved and used much stronger topological information on these moduli spaces show. So I've been a little bit vague here about how Q goes to infinity. And remember, there was also some implicit limit as something like the discriminant went to infinity, which here would be this genus going to infinity to show this match. For quadratic extensions, when G goes to infinity first and Q goes to infinity later, after, which might sound like a small change, but actually in terms of the difficulty of proving the result is a sort of a major step. Because if you remember, I said Q was like FQT. We would really like to be able to do this for a single Q that isn't traveling off to infinity. And so somehow, the later in the problem that you can send Q to infinity, the closer you are to getting of the question of most interest. And so this was for quadratic extensions. And yeah, also with Yuan Liu and David Zureick-Brown, we used, again, a study of moduli spaces of curves to show a match with the conjectures for general G So not just quadratic extensions, but arbitrary extensions, and this is a sort of q goes to infinity first result, and then again, while avoiding roots of unity. So this was also avoiding roots of unity, which occurs sort of in this way in this question. And so what was happening here, we zoom out and we were getting better, more and more information, at least as q goes to infinity, about the distribution of these class groups. And this is actually for the fundamental groups here. Okay, not just the abelianizations, the class groups. This is about the fundamental groups. We're getting more and more information about these distributions, but we couldn't see, we still didn't understand what was happening with roots of unity. And so part of that was because of the form of the information that we were getting. So what the algebraic geometry and topology gives, so understanding the algebraic geometry and topology of relevant moduli spaces occurring in this problem, they didn't tell you the probability that you get a particular group. It gives certain averages, okay? It gives certain averages over the distribution, which we call the moments. Okay, and so these moments, if we have here our random group, or the group that we have varying and we're trying to understand the distribution of, and I have some fixed group here, this is an average that we call the Beef moment. So the moments themselves are indexed by groups. And so this says what is the expectation or the average over the distribution. Remember, we're getting these class groups in some distribution. So what is the average number of surjective group homomorphisms from this group to a fixed group? And so these averages for many B or even all B are what this method gave. So when there were no roots of unity in the base field, one has a conjecture for the distributions, and we could find the moments of the conjectural distribution and even show that they determine the distribution. So one knew moments of the conjectural distributions and that they were determined by the moments. Indeed, one could get in our work moments in the case where there were roots of unity in the base field, but one had no idea what distribution those moments were coming from, what they were averages of, and couldn't then make much sense of them. I mean, even though you could see, okay, roots of unity are affecting these averages over the distribution, but what is going on? How is the distribution actually changing? And so that took us to another place. So section 2. Okay, so so in in looking at these questions, Sawin and I started thinking about analogous questions in the three-manifold situation. So just recalling that three manifolds are analogous to number fields and function fields. Because the latter have a three-dimensional homological duality called Artin-Verdier duality. So their cohomology has a three-dimensional duality, which is analogous to Poincare duality. So cohomologically, there are a lot of things similar, and so for us, coming from the number field and function field side, we thought of three manifolds as a good testing ground to try to understand some phenomena, and they are and they have a lot of advantages. The three manifolds have a lot of advantages because they are just much squishier. I mean, you can really do a lot of things with them that you can't do with number fields or curves over finite fields, which are so rigid. And in fact, so Dunfield and Thurston had in 2006 introduced a way of looking at distributions of three manifolds by taking a random Haggard splitting. So how do you do this? You take two solid genus G handle bodies. So these are solid three-dimensional manifolds with boundary. So these are two solid handle bodies. So that is not a three-manifold. However, if you glue the boundary of one to the boundary of the other, now there's no more boundary, and you have a compact oriented three-manifold. So if you can get, we'll say, a random three-manifold by gluing. And in fact, how are we going to glue? There are a lot of ways to glue a surface of genus G to a surface of genus G, and these are parameterized by the mapping class group. So by gluing the surfaces with a random element of the mapping class group, you can do, for example, pick some generators and do a long random walk. And there's an implicit limit there of the mapping class group, which is just recording the different ways to glue the surface of genus G to the surface of genus G, and you get three manifolds. And in fact, every three-manifold occurs this way as long as you let the genus be sufficiently large. They all have Haggard splittings, so we'll let the genus go to infinity as well. And so Dunfield and Thurston had introduced this way of getting random three-manifolds, and they had asked a lot of questions. They had asked a lot of questions about the distribution of the fundamental group, about the distribution of the fundamental group, which is, I just want to emphasize, precisely analogous to the questions about the distribution of the fundamental group of these curves over finite fields, or the analogous thing over number fields. And they had also asked, some of their questions were about the abelianization, so that's analogous via this analogy to the questions about class groups. And they did not have there were not many answers, but there were lots of questions. But one thing that they could do is compute moments, these average number of surjections to fixed groups, but it didn't, they weren't able to leverage that into to answers to their questions about the distribution, which feels a little bit like where this problem was stuck as well. In joint work with Will Sawin, very recently, we worked essentially on this moment problem, on trying to recover information about the distribution from these averages. So moment, I'll say it's moment problem work to describe a distribution from these averages. However, what we learned from the three-manifold case in trying to do this is that it was much better to study. So it turned out that it was much easier to study not the distribution of the fundamental groups themselves, but this just slightly different thing, the pair of the fundamental group with the class, the fundamental class of the three-manifold in the third homology of the fundamental group. So of course, the fundamental class first lives in the third homology of the manifold itself, but that has a map to the third group homology of the fundamental group. And so what is this? This is, instead of this being a group, this is, what do we think of this? This is a pair of group and an element in the third group homology of that group. And this arose very naturally in the case of three manifolds because, well, among other things, you have a natural class there that you're already thinking about. And so in fact, we found the moments of these pairs. So that looks like the expected number of surjections from the fundamental group that send the fundamental class to some particular class in the third homology of the target. All right, so this is like a pointed thing, except the point is a class in the third homology. So these are like refinements of these averages. This says how many surjections are there to B, and this says, well, how many surjections are there to B that's in the fundamental class of the three-manifold is some particular class in H3 of that group. And that and from that we could understand gives the distribution of these pairs, which in particular, once you understand the distribution of these pairs, you can forget the fundamental class, push it forward and understand the distribution of the fundamental groups themselves. But for our work to kind of turn the averages into a description of the distribution, that really, for that to work, it had to be on the distribution of pairs instead of groups from the beginning. And so one of the things that came out of this, once we had this distribution, for example, it answers, the questions that Dunfield and Thurston ask about the distribution. They ask very specific questions like, on average, how often this or that, and this just gives entirely the distribution, so it answers all of those kinds of questions. But it also showed that some properties of groups are probability zero. When you work out the distribution and then you see these formulas for how often things happen, sometimes those formulas work out to zero. And then you can ask yourself, okay, why did that happen? I mean, maybe it just happened because I let G go to infinity, there are infinitely many three-manifolds, and they sort of the ones with those fundamental groups disappeared because there were so few of them. But it could also be that just never occurs. And indeed, those properties we proved separately. These properties never occur. So I'll give you an example. So like an example statement, which is if the fundamental group of closed-oriented three-manifold has a symplectic irreducible representation over a finite field where Q is odd, then the dimension of the first group cohomology of the fundamental group with those coefficients is even. So that is a dimension of some vector space that could be even or odd a priori, and certainly there are plenty of finitely presented groups for which it's even and odd, but for a fundamental group of a three-manifold, this has to be even. So this is a new result about the fundamental groups of three-manifolds, and but one would have never realized it. I don't know how you would have come across it. At least nobody had so far, except that once we see that something is probability zero, it's very natural to go try to look specifically at that thing and see if it ever occurs. And so the things that we showed were the things that we saw happening were probability zero. We proved that those sort of never occur, which led us to so then this lets us characterize not the list of three-manifold groups, but the closure of three-manifold fundamental groups in some pro-finite topology, because we're really just studying finite quotients. And so one of the big takeaways from this was that if you discover something is happening with probability zero, which, you know, we weren't guessing it a priori, it worked out of, you know, numbers, explicit numbers for these averages, worked into explicit numbers for probabilities, and then those numbers sometimes, oh, that's zero. Okay, maybe there's a reason for that. So when that zero pops out, that leads you sort of naturally to prove, to want to prove, I mean, maybe you can, but in this case, we could prove that those things never occur. And so we also took back to number fields and function fields a lot of this strategy. So back to back to the function fields. I will just say, this let us address this sort of ongoing, we don't understand what's happening with roots of unity. I'll say the three manifolds are like number fields and function fields with all the roots of unity. So that was, that gave us kind of one extreme to understand, and now then we were trying to understand, okay, well, what happens when you only have in roots of unity? And so we used a similar strategy. So this led us to realize we need to use the fundamental class which you might call the Artin-Verdier duality class in the number field function field case. As we did in three manifolds to understand, and this is, you know, much less natural. If you're just asking about the class groups of number fields, you wouldn't necessarily think like, oh, okay, I want the class group with the, you know, with the image of the Artin-Verdier class in their third group homology. But indeed, that makes it much easier to understand what's going on. And then this in the function field analog. So again, as Q goes to infinity, we could, using this fundamental class, obtain the distribution with any number of roots of unity. So this all this through here, since there, I should say, is still joint work with Will Sawin with any number of roots of unity. And then sometimes one sees the probability zero, and then when probabilities are zero, we prove sort of those things never occur over number fields as well as function fields. So and that is an entirely new phenomena in the kind of conjectures. You don't see them anymore here, but if you remember that conjecture was like, we have everything occurs with some positive probability. So in particular, the conjectures were all of the flavor that everything occurs, but in fact, part of what's going on is when you have roots of unity in the base field, not everything can occur. There's some obstructions to what can occur that, I mean, this isn't like a perfect analogy, but you can think of it's, you know, of some flavor like this. So we see those zeros, they come out of, remember in the function field case, we had averages, we work out distributions, we see those zeros, but then now that we know what they are, we can prove, now that we know what we're looking for, we can prove that they never occur, even in the number field case, where we didn't have the averages came from the function field case. So we don't know anything about what does occur in the number field case, but at least the stuff that doesn't occur, we can prove doesn't occur, and then that helps us correct these conjectures that we're sort of saying everything occurs with some positive probability, just inversely proportional to automorphisms, we can say, well, no, it's not quite exactly that, like only certain things can occur. Indeed, we have precise formulas for them, and though I should say the formulas are nicest if you want to know how often something occurs with a particular class in its third homology group. You can always push that forward if you don't care about that. But part of what we learned here was that is an important invariant in understanding what's going on with these groups. All right, thanks. Yes.
In the analogy, function fields are more like mapping tori. If you would ask this same question, but instead of all three-manifold, just look at mapping tori, which are random doing mapping class.
Yeah, that's
the same answer.
That's a great question, right? Instead of gluing one handle body to another, we could take an interval over this surface and glue the two ends. And so I think that this method would indeed be able to find the distribution of those fundamental groups. And we haven't tried, but I think it's a great question. And and I think there's now a framework for understanding it. And it's interesting, it will be a distribution that will be closer. Of course, these fundamental groups, I mean, these say first homology groups all have a Z in them. So they're not general three-manifold, so it's a sort of something different on the three-manifold side. And those distributions will probably be absolutely closer to the distribution in the function field case, but they still will probably not be precisely on the nose the same somehow because, for a few different reasons, but including the fact that basically that these sort of have all the roots of unity and these will only ever have finally many roots of unity. And part of that, how that's coming in, is that this Artin-Verdier duality comes with a twist by the cyclotomic character. And so then how many roots of unity you have really affects that Artin-Verdier duality, whereas with Poincare duality, it just is what it is without any kind of cyclotomic character action. So it won't be, you won't have something that will be exactly the same as something in the function field case, but I think this would be a great example to understand, and it will probably certainly be closer to the distribution of groups you see over function fields.
In the interest of time, I think maybe we continue. Let's thank Melanie again for beautiful talk.